I know we were supposed to wrap up with linear algebra last time, but a few more comments. So remember, our underlying principle is we have our vector space U, and when we talk about spectral something, usually we're talking about linear transformations, because that's where spectrum comes into play. So a map from U back to itself. And last time we said, well, such maps can be associated with matrices. And so we have a matrix where here this value n you can call the dimension of your space, and because we're mapping from a space to itself, the input dimension is the same as the output dimension, so this makes a nice square matrix. And these entries here, well, it just depends on your vector space that you're working with, what's your underlying field, because vector spaces have underlying fields. But for us, we will essentially only deal with the reals. And in fact, the majority of the time we're going to deal with natural numbers, where here I let 0 be considered a natural number. And we said, well, we'd have to have these things, eigenvalues and eigenvectors. And so these eigenvectors are associated with the linear transformation. So they're not dependent on the matrix in some sense. We have this understanding that eigenvalues and eigenvectors are not matrix dependent, but of course, once we choose a matrix, the eigenvalue won't change, but the eigenvector might, because the matrix is chosen based on your basis, and so your basis representation may change. So our rule of thumb is we fix our matrix where we apply this eigenvector, which again is the stand-in for our transformation T, is some multiple of our vector. Now, how do we go from this to actually finding these numbers? Because, the first time you hear it, you say, well, that would be nice if they existed. And if they existed, could we even find them? Well, of course, there's a very simple procedure. You can start by rearranging this to say, well, lambda times v minus m times v should equal 0. And then we channel our Calc 1 students, say, well, yeah, you just factor out the v. And so lambda minus m times v should equal 0. And I say channel our inner Calc 1 students because, well, is this true? And how do we make it true? Of course, the answer should be it's not true, as written. What's missing? The identity. Yeah. So we slip in an identity matrix. So that way, we have, apples to apples comparison in some sense. And we say, okay, so what's really going on here? Well, there's a lot of language associated in linear algebra with this situation, this scenario. And we say, well, a non-zero vector times a matrix equals 0 says what? Well, if you think about what we said last time, when you multiply a matrix times a vector, you're really taking a linear combination of the columns. And so what we have is that some combination of the columns is 0. So we're rank deficient. We don't have a full set of linearly independent columns. And this is, of course, one of many ways of saying, there's something wrong with this matrix, and we call it singular. Now, for us, what we'll use is we'll say, okay, there's a long list of, many, many properties of what makes a matrix singular. We just mentioned one, and we just say, well, we scan our list and say, well, that tells us one of the things that must be true is that the determinant of this matrix must be 0. Where, when you think about what does a determinant do, if you think about of just a matrix itself, there is a nice geometrical interpretation of determinant, where it says start with a basic unit cube in your original space and apply the map and say, well, now what's the volume of it, or whatever the appropriate interpretation of volume is. And when you have linear dependence, essentially what happens is your cube collapses. Well, the nice thing is if you now think of lambda not as a fixed number but as a variable, then what you have is a polynomial. So we can call this p as a function of lambda. And this is the characteristic polynomial. And, well, when it comes to finding eigenvalues, what you can do is you find the roots. And once you find the roots, that's your eigenvalues. Now, there's some subtleties here. There's things such as your algebraic multiplicity, and that's how many times you have the roots, and then you have your geometric multiplicity, and that's how many times you have a vector. And these need not always be equal. Not always. So you have to understand, okay, well, what's the case when they're not equal, and what's the case when they are equal? And so we have to make sure we understand. Now, I will comment that for most graphs, and we haven't really defined matrices for graphs, when we talk about the eigenvalues, those are hard to compute because that means solving this characteristic polynomial. And solving characteristic polynomials, they aren't easy. Finding roots of polynomials in general are unpleasant. And so we'll be interested in eigenvalues which are nice, and there are some eigenvalues which have very nice properties and that we can actually solve for. But most eigenvalues are messy, and so there will be portions of the class where we say, well, let's not worry about the actual spectrum in terms of the eigenvalues. Let's worry about the spectrum in terms of characteristic polynomials. So there are times when we'll just jump back and forth, depending upon which one's more convenient. So the punchline here is that right down here, when we talk about the spectrum, that is the roots of your characteristic polynomial. And you count multiplicity. So in other words, if you have an eigenvalue that's repeated, then yes, I'm off the page. If you have a repeated eigenvalue, you make sure that you count that however many times you need to. And we said something out loud, but we should write it down for our notes, just in case. When we're in a very special case, so in particular, when we have symmetry, and that says aij equals aji, and we're keeping things real, which means, now I'm off the top. Okay, well, I'll have to work on my page here. So when we have symmetry and we keep things real, what's true? We mentioned this last time, but we should say it again out loud. What can we conclude?
That the eigenvalues are real.
Okay, all the eigenvalues are real. Good. What else can we conclude?
Diagonalizable.
Okay, well, all right. It's diagonalizable. That's a true statement. What about eigenvectors? Can we conclude anything about those?
They form a basis.
Well, what does it mean when they form a basis?
There's a linearly independent collection that spans the field.
Okay, all right. Well, in other words, we're not missing anything, is perhaps what we can say.
Okay.
And, all right, that is algebraic multiplicity is equal to geometric multiplicity. In other words, there's no shortage. But eigenvectors, are they guaranteed to be real?
Yes.
Are you sure?
No.
I'm not sure.
I think pretty sure. Yeah, because it's because MV equals lambda V. Like we would have to.
Yeah, you can take mv equals lambda v, and then you take the real and imaginary parts. And so the real part of an eigenvector satisfies mv equals lambda v. The imaginary part satisfies mv equals lambda v. So one of those is non-zero, and hence is also an eigenvector associated with that eigenvalue. So you can't assume your eigenvectors are real. One more fact. although you'll probably give me 2 or 3 before we get to the one we want.
Eigenvectors from different eigenspaces orthogonal.
Okay, good, yeah. So we can make, if lambda is not mu, our eigenvalues, then corresponding eigenvectors are perpendicular. And indeed, not only is that the case, but we can assume that all eigenvectors can be perpendicular. I'm not saying a priori, because if you have 2 things in the same eigenspace, you could choose a bad basis for that eigenspace. But you say, well, for that eigenspace, just make sure you choose things which are perpendicular. So these are things that are nice. So that's why we like those things. All right, so that's our last comment from wrapping up last time. So now to today. And for today, our goal is to talk about graphs, because we've talked about our spectral part, but that's only half of it, because it's spectral graph theory. So we need to talk about graphs. And as I mentioned, we do our little stroll through what is spectral graph theory, oftentimes when we think about a graph, we start by drawing pictures and we say, yeah, this is a graph. It's a picture. And you say, well, okay, is that really what a graph is? And maybe. But that's a representation. And so when we talk about a graph in an abstract sense, and we're not going to do this too often, oftentimes we will rely on pictures, and I don't want to discourage you from thinking about the pictures. I just want to remind ourselves where we're at. So when we think about a graph, it's really a pair of 2 things. And in particular, it's a pair of sets. So we have 2 sets called V and E. And where V, those are our vertices. And oftentimes, we don't really care too much about what our vertices are. They're just objects, and life is good. We work with that. Now, E is where things get more interesting. E, these are our edges. And the reason I say things get more interesting is because there's different ways we can think about edges, and the different ways we think about them lead to different types of graphs. And so almost all the times when we say, oh, here's this type of graph versus that type of graph, it all boils down to, what do you consider an edge? So as a very simple example, we'll call them simple graphs. Might as well start in the simple case. And what we think of that is E is some subset of, and this is notation that might seem strange, but when I say V, and upstairs I have this 2, that's just all the 2-element subsets of vertices. So it's all the possible pairs of vertices. Order doesn't matter. We could have directed graphs, and for that, order does matter. So I can think of it not as 2-element subsets, but I can think of them as 2-element list. And so V cross V, the Cartesian product of V and V. We can have weighted graphs, and these can be weighted simple graphs or weighted directed graphs. And in this case, what we think of is really, we don't have subsets. We think of E as being a function from V cross V into some space, let's say R. So we assign weights to the edges. And so now our weighted graphs, we have information. It's a lookup table to say how much weight do we have. Well, what else can we have? Hypergraphs. Now, hypergraphs get interesting. Now, what's a hypergraph? I guess I should define that.
You can vertices that are greater than 2.
Yeah, so this is a case where edges aren't just about 2 element sets. They could be 3 element sets. That's a 3 hypergraph. Or you could have 4 element sets. Or you could say, look, I'm not going to put a restriction. So maybe sometimes it's a 3 element set, maybe it's a 5 element set. And we could say E is some subset of 2 to the V. And then of course you can add extra restrictions. So these are 2 to the V is just all possible subsets of the vertices. And then of course you can add appropriate restrictions that you want, and so forth and so on. Most of our time, I would say, will be spent doing simple. We'll do a little bit of directed, so we'll put a little bit of a line around that. And so directed graphs, oftentimes, the way we're going to talk about directed graphs is we'll talk about the random walks. And we'll talk vaguely about weighted graphs, insofar as one of the things that we're going to talk about, and this is of course spoilers of what's coming up, is the distance matrix. And in that case, the entries of a distance matrix aren't simply like 0 or 1, they're numbers, and which correspond to a distance. So you could think of it as being a weight. And so that's why we can think of it in that way. And there's another thing that does come up, of course, which is you might say, well, do you have loops or do you not have loops? And, well, the answer is maybe. And of course, once you get into the matrix, then it really gets interesting. How do you treat a loop versus a non-loop? And I guess I should ask the question, what is a loop? Since I've said it. Okay, I see people are like, they're doing the rule. Yeah, so oftentimes that's how we think of it. It's something that connects back to itself. And you say, well, yeah, technically that wouldn't be part of a simple graph because you don't have 2 distinct vertices. And so you might say, okay, you have a simple graph, or you might say simple graph where we allow loops, or you might even say simple graph where there are no loops. And so if you read papers in graph theory, you'll see that sometimes in the first line or two, usually by the end of the introduction, they'll say, here's the assumption about what type of graph we're working with. So we're going to be working with simple graphs without loops. So that's a very common thing, and that's just because depending upon what type of graph you have, you're in a very different type of situation. I guess we should have drawn some example of a simple graph versus a directed graph at least. So what we have drawn, would be a simple graph now with a loop. A directed graph, visually the way you represent it, is you can add an arrow. And sometimes you'll hear people talk about oriented graphs versus directed graphs. And where oriented graphs, they have a restriction that says, if I have a vertex from U directed to V, that arrow, I can't have V going back to U. Whereas with directed graphs, you say, well, maybe you only have one way, but maybe you can have both ways. And you could say, well, aren't simple graphs just simply directed graphs where you just add in both directions? Yes, you could, but let's keep things simple. And so we usually don't say that. Now, again, as we go on further in spectral graph theory, these kinds of assumptions basically say, what kind of matrices do you want to consider? So simple graphs, we usually think of those as 0, 1 matrices, which are symmetric. Directed simple graphs, we say, well, we'll think of those as 0, 1 matrices, but we don't require symmetry. Weighted graphs, well, these are non-negative matrices. Hypergraphs, hopeless. No, I shouldn't say that. It's not completely hopeless. I mean, part of the question is, what's the right object to describe a hypergraph in spectral graph theory? And there's multidimensional arrays, and yes, you can do that, and there are ways to think about what it means to be an eigenvalue in that kind of setting. but sometimes they're not very efficient. And I heard a talk once by an academic sibling, and it was a really interesting talk. Said, oh, here's this way, you have this multidimensional array, you set everything up. And I was like, yeah, this is nice. I like this theory. And then at the end he said, well, and we have this example where there were 4 vertices and 6 edges, and it only took us 2 weeks to compute the eigenvalues. I'm like, okay, hopeless, forget it. You can't do anything with that. So, was there a question?
Yeah, you said non-negative for the weighted graphs,
Right.
but you wrote real.
Yeah, I did. Well, usually because the way we think of weighted graphs, I should have said real greater than or equal to 0, but you don't have to. If you don't put any restriction on, then as soon as you just say weighted graphs arbitrary, then now spectral graph theory has become linear algebra. And it's like, oh, okay. So most of the time when we think about weights in weighted graphs, they represent some sort of physical object, particularly things like flow. How much you can flow from one vertex to another, or capacity. And so those tend to be non-negative. So almost all examples that I know of that employ weighted graphs are non-negative.
Is that the same reasoning for why we're not over the complex numbers?
Pretty much. I mean, it's mostly just a matter of like, what's the interpretation?
Okay.
And is it a reasonable interpretation? Now, that being said, I have written papers where I have negative entries associated with edges in my matrix, and for very good reasons. And we'll at some point, I don't know if we'll talk about that explicitly, but we'll mention things where negative edge weights do make sense in talking about certain eigenvalues. But, yep. Any other questions?
Other directed hypergraphs?
Oh, yes. Yes. So, oftentimes the way people think about directed hypergraphs, now again, it's the linear algebra gets tricky, but in terms of graph theory itself, the way we often think about directed hypergraphs is we think about them as sort of marked edges. And we say, okay, I have an edge, and for each edge has some number of vertices, I'll mark a vertex. You can think of that as, I'll paint it red. And that's sort of like the arrow is pointing to that vertex. And so yes, there does exist this notion of directed hypergraphs. But I think as you keep adding extra layers, yes, you can describe more things, but there's a rule of thumb, right? Graph theory is amazingly broad insofar as you can pretty much describe anything, because everything has this sort of underlying how are things connected nature to it. But the more general you make something, the weaker the results you can say, because it has to apply everywhere. So the more assumptions you make at the beginning, then that helps you sort of narrow your focus, and then you can actually say something that potentially, fingers crossed, is a useful thing to say. One would hope. All right, so now we follow the tradition of graph theory, which is we spend a lot of time defining terms. Usually the first week or two of a graph theory class is, let's define 50 different things because we need to build up our language. And hopefully most of them aren't too bad. So for most of our work, think simple. All right, and so I'll put, again, just simple just to emphasize. All right, so let's start with some easy ones. U and V are adjacent. Adjacent if what is true? There's an edge. There's an edge from U to V. And so what we can say is when we think of a simple graph, we think of the edges as pairs. So we say, well, then the edge corresponding to the pair UV is an element of the edge set. All right. Now, U and E. So here, U and V are vertices. We sort of follow the tradition, the part of the alphabet near the letter U and V. Those are vertices. The part of the alphabet near the letter E is edges. Okay, so U, vertex U, edge E are incident if what is true? That is right. Vertex U is in lowercase e. Yes, have to be careful there. So the vertex U is in the edge. And so if we were to come over here and we can just label things U, V, here's W. U and V are adjacent. U and W are not. If I put it here in E, U is incident to E, as is V. V is also incident to E. Okay. Now, the next thing. So the degree. So the degree of vertex U, which we oftentimes will denote with degree of U. Sometimes we'll have multiple graphs at the same time, so we might add a subscript just to add clarification. And so how do you find the degree of a vertex? Okay, all right. So the degree of a vertex is number of edges it's in. So you can say it's the number of edges incidents to E. Good. Is there another way to think about it?
The number of adjacent vertices.
Right, it's the number of vertices.
As long as you don't have repeat edges.
Adjacent to, number of edges adjacent to U, and number of vertices adjacent to U. So yes, you mentioned repeat edges. We should have mentioned that. You have multigraphs, is when you have repetition. And so the question is, do you allow repeats? And we'll talk about things like that. Oftentimes, when you start hitting multigraphs, the way you handle that is with weighted graphs. Because you think of it as the number of repetitions is the weight. All right, so we are ready for Theorem 0. Every graph theory course always starts with the first theorem. It's always the same theorem. Does anybody know it? Sorry, what?
Handshake.
It's the handshake, yes. Do you remember what it says?
It's a theorem here.
Well, when is something a theorem versus when is something a lemma? I've actually had referee reports when they said, that's not a theorem. I'm like, what do you care? I mean, I can call it what I want. If that's the best thing you can complain about, it's not a bad paper. So okay, you call it the handshake lemma, yes. What is it?
Is it the sum of the degrees is twice the edges?
Yeah. So the sum of over all vertices, the degree of the vertex, is equal to 2 times the number of edges. All right. We will give a proof of this result. I'll try to fit it into this little space. I will fail, and then I'm going to feel really embarrassed. But this is not, let me emphasize, a spectral graph theory proof. Although it's going to feel like it. Because what I'm going to say is, look at the following matrix. And namely, look at the incidence matrix. Now, let's just think about, remember the goal for most mathematicians is to choose the wording so it makes sense. I said the word incidence matrix. What should that look like?
The rows correspond to vertices and the columns correspond to edges. Or maybe the other way around.
Yeah, we can pick. It doesn't matter. And what else?
It's 1 if they're incidence and 0 otherwise.
Yeah. So the incidence matrix should store incidences, which means that you should be looking at vertex edge interactions. And so, have you seen an incidence matrix before? You were just like, that's what I would do if I kept.
Seen an incidence matrix.
Okay, all right, good. Well, we won't officially do one because we're just gonna sort of abstract one. We'll probably do one for real at some point in time. The problem with incidence matrices is they tend to be very rectangular. So you have vertices and you have edges. Now, it doesn't really matter which one you pick. You can just pick your poison. And what do? Well, we have a vertex U, an edge E, and then we record. So this entry is 0 for not incident and 1 for incident. Okay, so here's going to be our proof. We're going to add up the entries in this matrix. Okay, so we're going to do it in 2 different ways. First off, suppose you add down a column. What are you going to get? Someone has held up their fingers. We're going to get 2, right? And why are we going to get 2? We're in simple graphs, and so each edge is incident with 2 vertices. Okay, good. Now, after we've added down the column, we're then going to add all the things that we tallied. What will we end up with? 2 times number of edges, because for each edge, that was a column, the sum of the column entries were 2, and we have number of edges, things that we add up, so we get 2 times the number of edges. Okay, well, now our second way, because that's how combinatorics works. You count things and then you count them again. And then hopefully you say, aha, I counted them correctly both times, something interesting happened. So now let's add across the rows first. So if I add across the rows, what happens?
Degree of each vertex.
You get the degree, right? Because you're capturing the incidences. So we'll get the degree of a vertex U. And now, after you've done that, add all those together, and what do you get? You get the sum of the degrees. And so you say, well, look, we just added all the entries in 2 different ways. We have to get the same number, so it must be the case that twice the number of edges is the sum of the degrees. I like this proof too. Why is this not a spectral graph theory proof? There's nothing about eigenvalues. There's not anything about linear transformations. This is, I could have called this, instead of an incidence matrix, I could have called it an incidence array. So this isn't a spectral graph theory, but it has a feeling of it. So in case you're wondering, like, when are we going to get to matrices? Steve's like, we already did. Ooh, So, all right, good. So, every class we should try to prove one thing, right? That's maybe. Okay. So a few other terms that are going to come up, and we will go through these. Walks in a graph. And these are not taken in any particular order. Okay, so we can just draw a graph here. That's a very friendly graph, yes? Sorry, that's some math humor. Do you know this?
It's a friendship graph.
It's a friendship graph. Yeah, it has a name. That's why it's a very friendly graph. Okay, so we'll add some more. All right.
That's what I was thinking. I didn't know that had a name.
Well, there's many graphs. Sometimes this is also called not now. Sometimes people, I think, call it the pinwheel graph or things like that. Okay, so walks in a graph. I'm gonna try to avoid too many writing things down, but I just want to make sure we understand what things are. So walks in a graph, we go from vertex U to vertex V, and each step moves along an edge. And for a walk, what other restriction do we have? Yeah, you're allowed to repeat. So walks are, that's it. You just have to get from U to V. And so if I wanted to, I could, of course, do all sorts of things. I'm not claiming at all anything about being the best walk in some sense. All right, so that's a walk in a graph. Sometimes people also talk about taking a path in a graph, but oftentimes walks are sufficient. Okay, when is a graph connected?
Everywhere from anywhere.
Right. Connected if for any pair U, V in the vertices of G, there is some walk between them. And again, we don't need to worry about efficiency. Okay, so what is the distance between U and V? Okay, good. So that is distance, oftentimes abbreviated distance, DIST, is the length of the shortest walk.
That is the number of edges.
Ah, yes. Equal number of edges. Yeah, well, this gets into interesting discussions about paths. I don't know if you've ever had that discussion about a path, but we haven't even defined what a path is, but there are people who have, I won't say heated arguments, lukewarm arguments about what's the right subscript to attach to a path, you know. Okay, so for instance, in this graph here, what's the distance between U and V? 2. What if I had a graph that wasn't connected? And I said, well, what's the distance between, say, U and W? Yeah. But generally speaking, by the time we pull out the distance, we're going to assume our graph is connected, because it's not good to have a matrix with entries that involve infinity. It doesn't feel good. All right. Well, since we've defined connected, what's a component of a graph?
Maximally connected subgraph.
Okay, good. And now you have another question. What's a subgraph?
A subset of V and subset of V. It doesn't have to be a reduced subgraph.
Oh, okay, now you've had another question. Subgraph and versus an induced subgraph.
A subset of V and a subset of the edges that only consist of elements of V.
Right.
So
Well, I could have G prime equals V prime E prime, where V prime is a subset of V, E prime is a subset of E. Is this enough to be a subgraph?
No, when you say that G prime is a graph itself.
Yeah, and G prime is a graph.
Oh, okay, that's fair.
You have to,
And E prime has to only be on that.
right, yeah. You have to have some, you want to make sure that your edges actually make sense. Okay, induced subgraph, Well, again, it's G prime is a subset of the vertices, a subset of the edges, and V prime is a subset of V. And what can we define as E prime?
E prime is all of the edges of E.
Right, all the edges of E that are available to us. So we can, one way to define it, this is not, I'm claiming a good way to define it, but one way to define it is take all your edges and you look at V prime 2. Remember, this is all your 2-element subsets. So it's just all possible edges that you could take.
You want equals, not subset.
Oh yeah, you're right.
Yes,
You're right. And do we need to worry about being a graph? No, it's just automatic because life is good. Okay, so good. So we have components, we have subgraphs, we have induced subgraphs. Let's see, what other things do we have? Oh, complements. Yes, that's something we should mention. What's the complement of a graph?
V to the 2 take away E.
Okay, all right, cool.
The graph on the same vertices that has all of the edges.
Exactly the opposite.
Yeah. So it's all the edges, you take out all the current edges, and then you put in all the ones that weren't there before. Or, there's lots of ways to say that. So you could say if G looks like V comma E, then G complement, which sometimes you see as a G bar or a G with a C, that looks like, it's the same set of vertices, and then you take all possible edges and remove the ones that were already there. So that's a set deletion. All right, good. There are other things that we can talk about, but this is a good collection of things. One of the things that we will talk about as we get going are things that you can do to graphs. So there will be things such as joins, products like a Cartesian product, tensor product, strong product. We'll be talking about blow-ups. But we still have a few minutes left. And so in our last few minutes, maybe we should quickly just do a rogues gallery, if you will, of graphs. Graphs that we're going to keep seeing again and again. So, what are famous graphs? You're trying to jump right to complicated ones. And so, okay, the Peterson graph is, yes, it shows up a lot. One of the reasons the Peterson graph shows up a lot, it's a lot of counterexamples to things. And it's also pretty to draw. There's lots of ways to draw. It's a graph on 10 vertices, and we will find its eigenvalues at some point in the next few weeks. So that's one way to draw it. All right. What are some other well-known graphs? Okay, so you have paths and P sub n, the dangerous part. And okay, so I'm going to label the vertices here. Sometimes we label vertices, sometimes we don't. I will say that for the most part, one of the goals in graph theories is that you want to focus on the actual structure of the graph, the connections. We don't really care about the labelings. And so almost everything in graph theory that's label dependent is uninteresting to us. We care about things which are label independent. So we don't want the labeling to matter. You may have remembered that there was a sort of a back and forth about what's the right subscript here. And so I will tell you that in some papers it's the number of vertices, in some papers it's the number of edges. I'd like to say that will be number of vertices consistent in our class. I hope that's true. We'll find out. Okay, so paths, what are some other things? Cycles, okay. And paths and cycles look very similar. The difference about a cycle is you just have an extra edge. And we could, of course, define all these things, but I think pictures are very compelling. Okay, other graphs. Okay, trees. Well, stuff. Okay, trees are connected acyclic. So it's sort of, trees are interesting in that they are the minimal way you can be connected. And there's some very beautiful results about trees in spectral graph theory. Okay, so while we're on trees, I'll mention stars. And that's, you have one central vertex connected to a bunch of other vertices. When you draw it this way, it doesn't look like a star. Yes, I'm still here. So this is its way of saying, hey, I've been on for 3 hours. Okay, I know, all right. Okay, a few others, since people wanted to jump to complicated ones. The complete graph, Kn, which does what?
Has all the edges.
Yes, has all possible edges, and hence it's complete. And that's why we put K for complete. Complete. Kn. What's a related one? The empty graph, good. What does the empty graph look like? Yes. It's just a bunch of isolated vertices. It turns out it's pretty easy to prove things about the empty graph. Complete bipartite. You can also do complete multipartite. And complete bipartite. And you have two sets of vertices. That's why it's bipartite, 2 parts. Complete, all possible edges in between. Okay, I know I'm almost out of time, so let me just mention 1 or 2 more. What about the cube graph?
Is this just any graph that can be written with binary labels, basically?
Well, there's an interesting question about isometric embedding. It's a very technical term about, when can you put something inside of a hyperdimensional cube. So the cube graph is literally not just this graph on 8 vertices. There are many other different graphs that you could draw of all dimensions, and we'll get into a formal definition of a cube graph. And one last quick question here. If I were to draw this graph, what if I put next to it the following graph? This is probably not the one you're thinking of. So this is a complete K44, but I've deleted a matching. And I haven't defined what a matching is, but essentially it's a set of disjoint edges. So I've deleted one maximum matching. What can you tell me about these 2 graphs?
Almost complements.
Well, no, not quite. Sorry, what? Yeah, these are the same graph. And that's why pictures can be misleading.
Right, it's bipartite because these have...
And it's not totally obvious when you look at it that they're the same, but they are in fact the same graph. And that's one of the challenges, and there's something called the graph isomorphism problem. If you hand me 2 graphs, are they the same graph? And we believe that that's hard. But spectral graph theory says, hey, here's one way that maybe you can answer it at least saying no.
Yeah.
Oftentimes it's easier to get a no than it is to get a yes. So, all right, with that, we'll stop.